didn't have to do that. I was in here on Friday.
If I don't update it, some point nags me again.
I'm talking about the reading.
Alright, hey. I'm gonna just open the top like this. You know what I'm saying? We got tiny pages. You gotta just put it in there. You know what I'm saying? This is a lot. Shove it in there. No, renegade quarter. Let's get this going, man. No, any combination. They accept credit. They might not give it back.
No, just in case. Just in case they want to it's pretty good card. Just don't tell anybody wrong. Just doing it now. This technically is my mother saying
They probably want to give like some
they had 0, they start taking 0 loss. Wait, no. No, I've used Theorem pretty well. That's like my joke. Wichita State has always been
maybe that's the kind of guy.
yeah. You almost know. Yeah. You see Irvine first question? I mean, how long is Virginia in the first round? You see Irvine beats Kentucky in the finals by 1 point.
Alright, more tomorrow, okay? I'm gonna ask you every day.
Kentucky's so good. The rest of the NCAA they're much better than Wichita State was.
Here is 4. Alright. Eminem. You guys are doing well today. You can decide if which who does what. Aren't they interesting problems? Right? Yeah. Which one are you taking?
I call A.
You call A? Alright. I got one over here. So it only gets to 2 deep.
Oh, so we're just looking at it.
No way. Next
I need an 89 or higher. Cycling, like 3 points.
Why are you trying to technology? Really? That's
Yeah, or doing exactly times 10.
Yeah.
Found the reverse question.
Yeah.
Is this fine with -1 half?
Oh, wait. Sorry.
Kind of fun to ask the reverse question here, isn't it?
Zero. Eight?
So what is she doing? Someone else explain. She's right. Oh, wait, hold up.
Wait, no. What'd I do? Did I simplify wrong?
You just didn't do anything with the third one. With the fourth. -1.
Negative what?
-3/4.
Okay. Oh, wait, I did. Oh, I see what you did. Sorry, my bad. Is that it?
We're
No.
multiplying by.
Oh, wait, factorial, so it's 6/8?
Yeah.
Yeah. Sorry.
What would that be? Someone said
Oh,
3/4.
okay.
There you go. Yeah, so it's kind of the reverse question we got here.
Do you have to put the negatives if in the rule it's like you're multiplying negative 1 to the n?
Yeah, I mean those are the derivatives, right? I mean this is by this is.
The rule just comes afterwards.
Yeah.
Thank you.
Yeah, there's no ambiguity here. Those are the answers. Anything else is wrong. Melanie, how's that second one? Is that coming along? So every coefficient, remember, the coefficient on x to the n is the nth derivative evaluated at 0 here, because we're sending to 0, which is exactly what we want, divided by n factorial. So you're going to multiply by n factorial on your series, and then you'll have whatever n is. Right? I know we kind of usually ask it the other way around, right? I give you the derivatives, you tell me the terms. But there's no reason we can't ask it this way. So no one's going to ask for some help from someone nearby, right? You're going to recruit someone nearby too to bounce an idea off. Because this is interesting, right? I'm not giving her a problem that we've ever done before. So if someone nearby, Melanie, has some insight for her, help her out. She's going to tell us what's up. Isn't this a fabulous question? Taking the derivative of that thing isn't too bad, right? I'll come back on the step.
Not this year, like.
Come back, part like 7. like
freezes up in front of
so
girls.
much.
Yeah. Cows are like the ultimate snack.
Everyone's just like, yeah, Angela, take her, get away. No.
Yeah.
It's just character.
What do you know? The derivative is 0.
You were saying it's like, yeah, last Carter his record. He was like, no, I have 15 other records. I don't mind lending one. And he said, I don't mind lending one. I just gotta take it back. One kid.
So, are you okay with that? Or you want to hunt for 3? Someone help us out with this one. You know, what's on the YouTube. I mean, I don't know what the rule for that is. I only heard it. Came out of my head. So we might need J prime. Okay, so that's what he's finding. Okay. Does everyone find J prime and J double prime? There's no X term. That's okay though, right? Is that okay that there's not I mean, the coefficient on X to the first is 0. There's no problem with that. Could you avoid finding the entire first and second derivative? You might be able to. But all we need is J prime of 0 and J double prime of 0. You could maybe do what we did in the in the first part of the world, right? If you wanted, right? You actually didn't find derivatives of this, did you? You could have. That would be or maybe we should say it the other way. You want to go back and solve A? Doing what Jake's doing right now, you actually take the first, second, third derivative of this guy up here and then plug in 0 and see what you get, right? That will work too. You'll see that it's n factorial times that. Anyway, see what feeling. I hope you see there are a couple ways to think about it. So, yeah, what do we require for a local extreme value? We require, if it's differentiable, which it certainly is, we require it to be 0. The derivative needs to be 0 there. If it's differentiable. So do you see that derivative of J is 0 at 0? And what else is true at 0? Its second derivative is positive. This is what Jake's writing. So what does that mean? If you have a tangent line and the derivative is second derivative is positive, that means J is concave up. So that must be at 0 a minimum. If you just like look at my hands in my picture, right? Like that's good. But we also like say by the second derivative test for extremes, you know. Does that make sense? I don't want you to forget the second derivative test for extremes. Remember that? Okay. Second derivative test is cool. Can't really use the first derivative test very easily here. I mean, you could actually. You could still plug in values into the derivative left and right at 0. You know, that would work actually. That would work. But this is cooler. I like this way. Yeah.
So it just has a local min at 0, and then we tell like why.
Yeah, at 0. Yeah. Yeah. Local min at 0. Yeah. Are there other minimums or maximums on this? I don't know. Think about that. Anything else on the warm you want to talk about? We don't have any homework to go over because we just took a quiz, and I think we're good with that. So we're going to just launch into something new today. Go ahead, Phil.
If there's a series where there's like positive, positive, negative, positive, positive, negative. Is there any way to find out like the rule for that?
Yeah, I mean, this one is definitely a lost cause as far as finding a rule because, like, we have no idea where this came from, and these are, like, terrible. You could maybe make a rule that comes, like, to generate these numbers, but I didn't have one in mind when I made it. That's for sure. Right, so. yeah, let's say it again. There's not always, when we ask, if we ever ask you for the general term or for the rule in summation notation or whatever, we'll try to make one that like is doable, right? Some are either really hard or impossible, like this one, right? I don't know. It's not obvious at all what the rule would be here. Okay. So today we talked about, we're moving on to section 9.3. Taylor's theorem is the name of the section in the book. And in particular, we're very concerned with we're finally turning our attention to the error that these approximations can give you when you truncate a series somewhere. That's kind of the goal of today, is to kind of think about, because sometimes all we have is a Taylor series, right? We don't maybe even know what the function it came from was. Can we still make some kind of conjecture about how close it is to the original function, right? How good are these? Maybe these are terrible. Like, why are we using them? You know, maybe they're good. When are they good? So we'll start with this this function, and we'll talk about the error in it too. I hope the coming up with the Taylor series is not bad, but we can do it together again as a good example. Oops. So what do we have? E to the whatever, right? E to the u has its power series expansion as 1 plus u plus u squared over 2 plus u cubed over 3 factorial plus u to the 4th over 4 factorial. And I'm gonna stop there. You see why? Because it says 4th order, and we're going to be just sticking in negative 2x into this. So this is how I might think about it. You could also rederive it from first principles if you like, and you'll get the same answer. Okay? It says centered at 0, so I think we're good. Here we go. 1 minus 2x. We'll simplify it all together here. So it would be 4x squared over 2 minus 8x cubed over 3 factorial plus 16x to the 4th over 4 factorial. And those could actually be simplified some more, huh? Okay, so the truncated version of this at the 4th order term, we might call P4 or something like that, or T4, you know, some polynomial subscript 4. And then plug in 0.2 to that. And someone do that now on the calculator. I can pull my calculator out too, but you know, this is not meant to be the hard part. And also compute, you know, so compute that we want to compare, that is, the following two results. The 4th order Taylor polynomial versus e to the negative 2x, right? And we're going to plug in 0.2 into both of these, please, and see how they compare. This first one comes out to what? And this second one comes out to what? Let's see what those two values are. Just for fun, I might put this in y1. I don't know. Might need it. You never know. I know, I'm just checking all my work here. Minus 8x cubed over 6. Yeah, thank you. There we go, all right. And here I'll put in, you don't have to put it in, you can just do it on your home screen too. I just thought maybe I'll need it again, so I'll put them both in here. Okay, so vars, y vars function y1 of 0.2. How do they compare? They're decent? Ooh, not bad, right? In fact, just to be really clear, we could do this, right? 0.2 minus, you could actually subtract these two. You get, this would be like the error. How far off are we? Like, we're on the order of 10 to the negative 5th power, right? As far as our error goes. So it's good, it's really good. Okay, so that's one way to think about error. Certainly if you have access to the function and you have access to the power series, then we can write these two things down. Here, I'll get these off the calculator here. So we got 0.6704 and 0.6703. To write some more decimal places just for fun. 20046, and you can subtract and find the error. Yeah. Any questions so far? This is just trying to start the discussion about how far off we can be. So this is just the first kind of way we might think about it. Have we done this before? I mean, a little bit, maybe not really. E to the negative 2 times e to the x. No, e to the, wait, is it? That's not what we had though. Rules of exponents, careful. We have e to the x to the negative second power, right? So you could take power series for e to the x and raise the whole thing to the negative second power. Well, how do you do that? I don't know. You with me on that? I think you're right. What you just said would be.
Well, I guess so I messed up on that part, but
Yeah.
I plugged it into the calculator and I get exactly 0.67.
Yeah, which one did you do? Oh,
The
yeah.
one with the negative 2, you took negative 2 times
And you used I mean, those things that shouldn't be equal. I don't know. E to the negative 2 times e to the x is not the same thing as e to the negative 2x, right?
But then where did I get exactly
I don't know. But in general, that's not like a thing, something that would work. I don't know. Try it for another number, see if they compare and see if they come out to be the same. I'd be curious. I don't see why that would be true, but. All right, so we should start building some more powerful tools into our tool belt here, okay? So this is Taylor's theorem, and you might think, oh, we already heard Taylor's theorem. Well, we did kind of, right? So this should be familiar. All of this first part, all the way up to here, right? All these are what you expect, right? Nth derivative evaluate the center of our expansion divided by n factorial. And then what we're saying here, here's the new part though, right? We're saying that f of x equals this, and there's no triple dot at the end of this, right? This is truncated. You understand? This is a finite series, and it equals the original function. That is not what we've been doing recently. Haven't we always said, well, if you were to go on and let this be an infinite polynomial, then it would equal the original function, right? So how is this different? Well, it's different because of this little guy down here, right? So we have the Taylor series, the truncated series, right, of order n here, and then plus whatever this is, and R stands for the remainder, right? So this is the remainder. So whatever. So you're like, okay, well that's kind of dumb. Of course, it's going to equal. It's going to equal it now because it's like whatever it was before. You know, plus the amount we're off by. Of course, that's going to correct for our error because it's like designed to do that. That's what you call it. You call it the remainder term. But the thing that's surprising is that the remainder takes on the form of the next term. Do you see this? So the next term in the expansion, we're saying that Taylor series has at most an error of, excuse me, the exact error is this value right here. Now there's one little thing in here. There's a C value in here. And so we're saying that the next term, not evaluated at the center, A, which is where we normally evaluate them, but somewhere else in this interval is the thing you have to do to correct your error, right? And this C value, this is like an existence. This should feel a little bit, in fact we used C, I think, didn't we, when we did the mean value theorem? This should feel a little bit like the existence style result that we presented when we talked about the mean value theorem. We said there exists some C value in some interval that takes on the average slope between two, right? Takes on the average rate of change. You remember that? The mean value theorem? We didn't say where it was, we could find it. And likewise, you could find the value of C that makes this happen for any given thing. But it's an existence proof, yeah. Sure, sorry, I just pushed the button here. Sorry, I accidentally pushed the button. There you go, sorry, I got excited. wasn't even looking. Yeah, so this is called, this remainder here is the thing we're kind of honing in on today. It's called the Lagrange form of the remainder. And it, like I said, it should make sense. It's like, oh, something to memorize. But not really, it's just the next term, right? Evaluate, though, this is the one trick, evaluate not at the center, but at somewhere else. And we're guaranteeing that there always exists some value that will make this an equality. You know, that will correct whatever error is left in the infinite number of terms that we haven't listed. That's pretty remarkable that that would always happen. In fact, this doesn't just feel like the mean value theorem. It is the mean value theorem. Are you ready? For the very, very trivial result here, where I cover all this up, what is the remainder? The remainder is this, where it's the first derivative evaluated at some c value, and if you rearrange the terms, you will get the mean value theorem. Yeah, so this is actually the mean value theorem like on steroids. So if you cover up all the higher order terms except for the constant, and then you apply this remainder, you get the mean value theorem. Okay? So there always is a c value that kind of corrects for the error, is a good way to say it. There's a lot to swallow, right? There's a lot of A's and C's and stuff. Do you understand the claim we're making? Okay. So in particular, what that says is we don't maybe know where that C value is, but we do kind of have a sense of how much that, what this term could be in its greatest form. This value up here, what's the biggest it could be? This next derivative at C, how big could it be? That's a good question. On the interval of interest, that's a question we might be able to answer. So let's call that largest value of the next derivative. No, it won't be that big actually, right? But let's call that value m. That's the largest, and we're going to take that value m to be the largest value of the next derivative, right? In absolute value, so as big positive or as big negative as it could be, on the interval of interest, right? How big could be? How could, you know, this is the Lagrange form of the remainder we just looked at, right? Just a second ago. But instead of like talking about some existence, we're actually bringing this down home now. How big could the error be on this interval? Forget what C could be or whatever. This is the largest it could be. Let's see. Oh yeah, you know. Yeah, we want to hear our names right at the end of the thing. All right, more tomorrow. Stop talking about other teachers. They don't have any. Okay. No context. All right, so just to be clear, sorry, I should put these up again. Just to be clear, A is, remember that it's because it's hard to understand. What are we talking about? The error in what? What are we approximating again? Remember, we're approximating at the value x, okay? So if you're asking what's the biggest error we could have at some x value, then that's what we're talking about, that x value. And remember, our series is centered at A, or whatever series we're looking at. Hopefully you still know that. So hopefully, is there any letter up there that you're confused about? Any subscript, any notation at all? This is easy to get lost. This is a little bit intense. That's it.
Why did you use T instead of C in the
So C, there exists some C value that corrects for the error, right? So, I mean, you could say C here. It's just a little bit of a matter of taste. But C doesn't range. There is some C value, and it's fixed, right? We know it exists, but we don't always know what it is. So, whenever I say C, I think of like one particular value. But whenever I say T, I'm thinking of like, I'm letting that be anything. Does that make sense?
So when you say
I think of C as a constant.
it's a constant.
The T is a variable. Yeah. So I just want to make that distinction. Right. There is a T value somewhere in here that will, when T will be C, whatever C is. Right. That was a great question. It's hard to Yeah, understand. Why do I have a t in there suddenly? Okay. How do we figure this out? What the maximum value of the n plus 1 derivative is on the interval of interest? Well, I mean, sometimes we can kind of graph it and we can kind of think about it, but it's not always easy, you know. And then just one word. This is just a little bit different than the formula in the book. You're welcome to look at it. It won't confuse you too much. It's just got a little bit of a different thing happening here. But this is the form that we care about, and it's easier. I just trust you on that. Okay. So let's look at our example from earlier. Here's the power series we did earlier, and we approximated this value, P4 of 0.2. And it's approximately, this is the full value of the actual function, e to the negative 2x, right? So this is what the previous theorem we just put up on the slide guarantees, right? We actually happen to know, because we have access to the original function and our series, we can calculate what the error is. There's no question about that. But say we didn't. Could we come up with the error in this? Right? Could we say something about how far off we were? Yeah. So let's talk about on the interval 0 to 0.2, how big our error could be on the interval 0 to 0.2. So what the previous theorem says is it will be no greater than the following thing, where m equals 32, and I'm just going to tell you, but we can justify this with a little picture off the side or something like that, is the maximum value of the fifth derivative, which we didn't actually ever compute, did we? We should maybe write it off to the side here. The next term, if we were to have one more term, would be of the form negative 2x to the fifth over 5 factorial, right? Right, that would be the next term. So we get the nth, so what is the nth derivative here? Well, maybe you'll have to justify that this is what we get here. Yeah, you see where the negative 32 e to the negative 2x is coming from? Yeah.
Yeah, like, I was thinking of why we can match this. Like, you can only put positive x digits and you still have a negative out no matter what. So you get something less than the absolute value, right?
You know, let me think about what you just said. So you're saying if you put in,
Because
oh yeah, this up here you mean?
No, I was talking about where
This will always be positive, that's true. We don't need these absolute values.
I was talking about
Down here.
Like why that would be the maximum, because like if you have a positive thing, positive x, and it's still a negative x.
Yeah, in order, like I said, you can just trust me that the max is 32. You could graph it in your calculator. Or let's actually try and get a picture of this real quick. It's an exponential decay function, so it looks like this. Oh wait, it's got a negative in front of it, but we're going to make it an absolute value, so you could make it flip it up if you wanted. So it's where is the maximum value of this gonna lie? Where is it gonna look? What is it gonna look like? Like I said, if you wanted to draw it like this, you could, because it's the absolute value of that exponential decay function.
Yeah.
So where is on the interval 0 to 0.2? Where will the biggest value be on the interval 0 to 0.2? It'll be at 0, won't it? So is it obvious if you put 0 into this, you get 32? Okay. So that one's not too bad actually, even without a calculator to say, oh yeah, it's 32. Eventually you'll need a calculator anyway though, because we're about to compute this. Okay. So, but the point is, this is as big as the error could possibly be. If you're approximating a value of this function, if you want this to be the function up here, this polynomial, you're all about using the fourth order polynomial instead of our function. Okay, that's not a problem. On the interval, if you're approximating values for x in between 0 and 0.2, you'll never be off. Isn't this amazing? You'll never be off by more than this amount right here. That's what we're saying, right? That's the maximum you could ever possibly be off if you're using this function instead of our actual function on the interval 0 to 0.2. Is that clear? And you saw the question, go ahead.
Will you ever give us
The n value?
N. Like, will we be given?
Sometimes, yeah. Sometimes just to quicken your work, we'll say, by the way, m is this, right? But sometimes you need to compute it, right? So I'm going to work under the assumption as we move forward today, right? And Avish, is this coming through to you? Does it make sense? Okay, yeah. Okay, all right. Take that. All right. Let's be polite. All right. how about this one? We've only worked with that one again today so far. By the way, this is one of the series that's, I think, listed in your book as one of our like common ones. It's actually got a really nice power series expansion, and we'll find it here if we need to. I've given you the first two terms. There are lots of ways we can ask this question. So, what interval are we interested in now? Did I give you an interval? I did. On the interval negative to positive 0.1, right? Is that clear? I've said that in an interesting way, but I'm interested in approximating this series is centered where? This series is centered at 0, so we're okay, right? We're gonna have our a value is 0. That's our center, and we're interested on the interval from negative to positive 1.1. 0.1. Okay. Yeah.
So we're using the second order only, or is that?
Yeah, it says find the error when we substitute, like we don't want this function, we want to use this function for whatever reason. How bad are we going to be in doing that? How careless are we when we do that? So I'm going to compute the first 3 derivatives of f. Can you tell me why I'm doing it? What? Wait, the first 3 derivatives. Wait, what? Why? Yeah, we need the n plus first derivative, don't we? Because we're going to evaluate that derivative. We're going to try and think about what its maximum will be on the interval of interest. All right, then we need to find the maximum of this function on the interval negative 0.1 to 0.1. So again, we can kind of think really hard about what the absolute value of this function looks like, maybe. Right? I think I know there's an asymptote at negative 1. I mean, maybe I can reason through what this looks like. Or actually, on this one, why don't we resort to graphing in our calculator? I think you could reason through it, but let's just pull up a picture of it right now. We have a calculator handy. So we have the math absolute value of 2 times 1 plus x to the negative third. I guess we could have done whatever, you know. Does that work? 2 times 1 plus x to the negative third. Absolute value of all that. And actually, why don't we restrict my window to be negative 0.1 to 0.1? How about that? Right? Isn't that what we want? And I'll adjust my y min and y max if I need to, I guess. Right now, I might happen, because of the last thing I happen to do on this calculator, I guess I have it negative and positive 4. You can just do zoom fit, too, if you want. Let's take a look at this guy. And actually, we don't need any negative y values, do we? Let's just do the absolute value of this thing. All right, so where is that at its largest on this interval? Is it clear that it's at the left endpoint? Yeah. That's tricky to think through without your calculator. You could look at this function as a global thing, and actually I think you could do it. You could reason through the fact that, oh yeah, okay, I know this function is decreasing, and the absolute value of this function rather is decreasing. Yeah, so it's tricky, but one way or another we need to establish what that value is. Let's actually compute it. Negative 0.1. 2.7434842. That's our m value, our capital M value, right? That's the largest. We don't know what c value. We don't know what c value fixes this perfectly, but we do know the largest error we could possibly have coming from this derivative is this. This is the biggest the derivative could even be, right? So here's our absolute error, right? That value I got off the calculator is that, and then we compute the error using that value. That makes sense? So this coming up with the big M, is a little bit, that's the hard part here, right? The other part of the error is easy. That's always the same. It's always, right? But this piece is coming up with the M value is very tricky. And that's why someone was asking, if we ever give you the M value, sometimes to quicken the work we just say like, right? You have to find the M value by yourself. You have to find the third derivative or the whatever. And then you have to figure out, you have to analyze that third derivative in the way we just did. It's complicated, right? But just I think it's worth saying again. What have we just done? we've just said that if someone uses this little quadratic polynomial, right? It's nice. It's just a little cute little polynomial instead of this guy. On the interval negative to positive 0.1, we will never be off by more than 0.000457, whatever, right? That's the biggest we could ever be off by. You see how powerful a result this is? We can say something about, with definite, something very definite about something that seems very kind of hard to say something definite about. So just as an example, we just found the maximum error to be this. Let's check the actual error of the function at the endpoint. So let's actually use the natural log of 1 plus x and see what we get. So here's my side-by-side comparison at the endpoints, right? You can check other places in between. The endpoints are the ones that have, for this particular function, the endpoints are where this is most extreme. Will the m value always be at an endpoint? Is that where the maximum value of that derivative will always be? It turns out that that's what happened here today. But it's not always going to be true. It depends what your third derivative, whatever you're looking at, will look like. So here's our x value. Here's the actual f of x value. Here's our polynomial approximation. And here are the two errors at the endpoints, just as an example. You can check other places if you like. And aren't those less than the error we claimed it would always be less than? Okay. You can actually compute the difference in these two functions and see what the error is. Yeah.
How do you know how many derivatives we have to take?
So if we're talking about on this one, we were using the second order polynomial to do the approximation. Well, that means you need to think about the third, right? The error term, the Lagrange error term, has the form of the n plus first term of the Taylor series expansion. Okay. Questions, comments about that? We have a couple minutes, so feel free. We want to go back to a slide. This is a hard idea. Love to. By the way, just for fun, I've been recording my lectures. If you want to see this again today, it'll be on YouTube. Yeah. I'm just trying it out, just for fun.
So,
I'm trying to be a star. Yeah.
The absolute value of x minus a, why did you use 0.1 for x?
Yeah, why do we use 0.1 for x?
Because it doesn't matter whether you use negative 0.1 or 0.1, because that's not where the max is.
Yeah, so x is so a is the center of your interval, and x is the farthest away you are on the interval, right? So in this case, it's 0.1, right?
Okay.
But could it be negative 0.1? What would happen if you put negative 0.1 in? You tell me. It'd be the same thing, right? So yeah, does that make sense? That's a great question. I don't think we stopped to say that. So thank you. All right. If you have another question, let me know. But hopefully you've gained some appreciation for how to compute error today.